divide these two numbers, but I want you to do it old school, like this. How long has it been since you've done that? Long time? All right, the reason I have you do this is we're going to learn to do this with polynomials. And the reason you wrote the numbers in each spot like you did, even though it may have been a very long time since you've done it, there was a reason. So first thing I want to ask, why is there no number above the 1? Because 5 doesn't go into 1, right? We needed to move over to have enough. We need to be able to multiply. We put a 2 up here because 2 times 5 gives us 10. That was the only, and that was the smallest amount or biggest amount we could get in there. And then we had to subtract or change the sign. Got to the 2, made sure we had this, and then pull down 1, so we had the same number of terms. And then once we got there, we just kind of continued repeating the first process over and over. Did everybody get this answer? And no remainder, right? Why is there no remainder? Because we got in a 0 down there, right? Well, what we're going to do is we're going to take this same process of long division. We're going to do it with polynomials. And it works the same way. And the reason I had you do this is it's probably been years since you've actually done one of those on a piece of paper, right? You're to the point to where if I needed to divide those two numbers to use it for something, I'll plug it in my calculator and move on because I know how to do it. I don't need to practice it every single time. So let's write this out. So I want to take x minus 2, figure out how many times it goes into x to the third plus 3x squared minus 4x minus 12. So let's write that down. Taking the same thing like I did here, and I'm just doing it with polynomials now. The process actually works the same. I'm going to break this down into smaller pieces, like I'm going to start by subtracting this 10. I'm going to do the same thing here, match up the same number of terms so I can make this work. So how many terms does our divisor have? X minus 2 is a binomial. It is 2 terms, right? So just like we didn't start directly over top of the 1 here, I'm not going to start writing anything until I get over here. Because I need 2 spaces, right? 2 terms, 2 spaces to write both the terms because I need a number that I'm going to multiply here to write underneath. Now what we miss when we do this, what happened to this 1? It canceled out, really. It turned into nothing because 1 minus 1 was a 0. We're going to make the same thing happen here. We're eventually going to get down and we're going to subtract when we find out what 2 terms to write here. What we're going to force to happen is, I know that this front term, just like it happened here in every single one of these, if you look down, every one of these, this front term did what? We made it cancel out. That was how we picked what we multiplied on the top by. We're going to use that same premise to drive this forward. What number do I want right here? I want this. I shouldn't say number. What term do I want right here? How do I get x to the third to cancel out? I subtract it by x to the third. Right? That'll give me my 0, just like I did in the beginning. What has to go up here to make that multiplication happen? Something times x gives me x to the third, because why was the 1 right here? Because 5 times 2 was 10. It gave me the first term that I wanted of a 1. How do I make, what do I need to do to this x? What do I need to multiply it by to turn it into x to the third? I need to multiply it by x squared. X squared times x gives me x to the third, and that's going to give me the 0 that I want right there when I subtract them. Now, just like we did here, this other number is whatever happens when we do this multiplication. So what is x squared times negative 2? That's negative 2x squared. Now this is where this gets weird. X to the third minus x to the third is 0. That's what we wanted. But we've got to be really cautious with this. What is 3x squared minus negative 2x squared? That's a positive 5x squared because we're subtracting a negative. Notice that I put parentheses around this. Okay? So the 0 is there, that's fine. The next step was to pull down the next term, so we had 2. And we are going to subtract. Now we need to make the numbers match again. So what needs to go underneath the 5x squared? Another 5x squared. So now when I work backwards, what do I need to multiply x by to get 5x squared? Well, I know the first thing needs to be a 5. Because 5 times 1 will give you the 5. How many more x's do I need? I just need 1, that's right. X times x is x squared. That will make that first term what I want it to be, so I get 0 here. Now we do the second multiplication to fill in here. 5x squared minus 5x times negative 2. And now negative 4 minus negative 10. Anybody agree? Is it positive or is it negative?
Positive.
Because you're doing negative 4 minus negative 10. Remember, minusing a negative turns it into a positive. Pull down the last term. You get a minus 12. Draw our subtraction again. We know that this first thing needs to be 6x. We already have the x, so we're good there. But this is a 1, so that means this needs to be a 6. Because 6 times x will give me my 6x. 6 times negative 2 is negative 12, so we know this is 0. Negative 12 minus negative 12.
12.
So when we did this division, what we found out is that this, I'm going to write it out, x to the third plus 3x squared minus 4x minus 12. Well, I'm still going to run out of room. We found out that this was equal to x squared plus 5x plus 6. Now you think back to where we learned this. This is just another scaffolding for the same thing that we learned doing in the box, okay? This told me that answer. When we did this with a box, what we did, we drew the box, and we wrote the answer that we had, this part, underneath. We drew our rows, and we put this on the outside, and then the answer was this stuff on the top, which you're going to get the same thing as what we had here. And what happened is, remember multiplying, you'd fill them in backwards. This had to be x to the third. X times what gives you x to the third? X squared. That was minus 2x. We added the diagonals. I will go through a whole example on this later. But what I wanted to show you, these two things are the same thing, just written in a different orientation. You're still dividing stuff. Do you remember doing these things with the boxes before? Okay. Part of the reason we go over the long division process, I want you to know that it's there so that when you say you were to get confused on some of the division stuff and you were to do your own search on YouTube or anything else and look for stuff, there's about a 60% chance you're going to see somebody doing this. Which if you've never seen it before, you'd have, okay, that's nothing of what I'm looking for, but it actually is. It's just, you've got to be cautious with it, okay? Could you recreate this process for me? Could you do it again? Try it. I want you to try that one. I did it both ways. I did it with the box and I did it with long division, okay? And let's be honest, when you do your quizzes and your other stuff like that where we practice the division, am I going to be able to have you necessarily show me exactly what you did with the way our quizzes are anymore? But I want you to be able to tackle both methods. But this is also one of those that I tell you at this point, you pick one that works better for you. If the box works and you can find your remainders easy, that's fine. I like the long division when there's a remainder, because I feel that it's much easier to see that remainder when it's done than having to draw that extra box. But be as proficient as you can to be able to at least work your way through both of them so you've seen them. I'm sure that you'll have your preference of, if I had to divide a polynomial for a quiz, I'm going to do the box every time because I practice it more. I have no problems with that. You might say, now that I've seen long division, I think it laid out better. You could use that every time, but be able to see both of them. So worked my way through. Anyways, the one with the box, everything in red is the given stuff. We're given that this is what we're dividing. We're given this is what we want to divide by. And this 2x to the third always starts in this upper corner. The way that this box works as we go through and we divide, this 2x squared is because that's what we need when we multiply these two together to find this answer that we were given. We have to have 2x squared because 2x squared times x gives me 2x to the third. So I find this top part first. Then I multiply this and the -3 to find the bottom corner. And I use that answer to work my way back up here, because I know that this diagonal has to add to +4. That was part of my answer. -6 and 10 give you the +4 you need with the x squared. Then you're back at the top in the middle. You can find the top, find the bottom, find the diagonal, top, bottom. I'm sure if you practiced a couple of those, you would remember that from when we did it in Math 3, okay? Did anybody get that one right? I didn't give you a ton of time. We're going to talk about two theorems that go with this. We're going to talk about what's called the factor and the remainder theorem. So let's talk factors first. Is x minus 3 a factor of the bigger polynomial? Well, let me go back and ask you this. Is 5 a factor of 12,375? Why?
Because it goes into it.
Because it goes in evenly. That's right. And then that means that what type of remainder do we have? We have 0. Our ultimate goal is going to be to factor polynomials so we can sketch them. And the way that we test roots to see if they work is we do this division. And what we're hunting for is we're hunting for these remainders down here that are 0. If we get a remainder of 0, that means that something is a factor. And we can see that with the numbers. 5 was a factor of 12,375 because it had no remainder. Is x minus 3 a factor of the other one? No, because we had a remainder. Okay? Now, the division is going to be necessary for our steps because we're eventually going to completely factor polynomials. But it's not the only way that we can go through and determine if something is a factor. There's two little theorems that are actually pretty close to the same thing that tell us about this. One of them is called the factor theorem. It says in a polynomial p of x, which for this example would be this. That's our p of x. X minus a is a factor if and only if p of a equals 0. So this is x minus a. So therefore, what is a equal to? A is equal to 2. Got to be careful the signs, but you got to solve it and find what the x equals would be. And what this is saying is take this and actually plug it into the polynomial, meaning all those x's become 2. So make all those x's 2. And let's look and see what happens. What is 2 to the third? 2 to the third is 8, right? What is 3 times 2? That's 6. Then we get a negative 8, and that 12 doesn't change. What do we see this equals to? It equals 0, which is when we talked about factors, right? It's what we were hunting. If you could take your x equals value from the root you're trying to test, plug it into the polynomial that you want to know if it's a factor of, you get 0 out of that polynomial, it will tell you, that tells you that it is a factor of it. Because we're hunting x-intercepts here. That's what factors are. If x minus 2 is an x-intercept, right? That means the x value of that coordinate is 2. To be on the x-axis, what does your y value have to be? Your y value has to be 0. Think points. If we were making this sketch and we knew that that was an x-intercept, that's what we just found out, right? It means that its x-coordinate is 2 and its y-coordinate is 0. We're graphing this polynomial, meaning when we plug that 2 into it, if it's an x-intercept, we should get 0. It makes sense, okay? Now they give, it says another name, but to me it's really the same thing. They call this the remainder theorem. What I want you to do, I want you to test this same idea with this one. Let's make this p of x. That means this is our x minus a, right? So our a value is a positive 3. What happens when you plug in 3 into that polynomial? Do the math. Plug it into Desmos and plug it into your calculator, see what you get as an answer. So I mean 2, 3 to the third, 4, 3 squared plus 5. Let's see, this is 2 times 27, 4 times 9 plus 5, right? So 40, 54, right? What'd you get?
I think I did it wrong.
What was your final answer?
70.
54 plus 36 is 90, plus 5 is?
Yeah, that's not right.
How does that relate to the divisions?
There's your remainder.
It's the remainder. Because remember, we hunted factors. If we got a remainder of 0, that meant that it was a factor. What we're doing here by plugging these values in, we're actually finding the remainder from our division each time. And that's what the remainder theorem says. If you plug in the a value, it'll tell you the remainder that's supposed to be left. Which is exactly what we were doing here when we talked about it as the factor theorem. We were looking for the remainder, and we were trying to figure out if the remainder was 0. And all this factor theorem says is, hey, when you test to find the remainder, if you get a remainder of 0, that means it has to be a factor. It has to work. And I promise you this is leading somewhere as we work into really factoring polynomials, okay? One other quick thing about division, and then we're going to be done, okay? And this one you're going to like, I promise. We're going to talk about synthetic division. Same goal. We're going to divide this polynomial. But like anything that you do repetitively, right, you want to make it quicker. And that's what this actually does, is it's going to make the drawing the box and doing the long division seem ridiculously long compared to what we're about to learn. So this is a shorthand for dividing a polynomial by x minus a. So this is my x minus a. This was that p of x, the polynomial I wanted to divide. It's similar to long division, but will only work with the coefficients. So there's a couple steps with this. First step, write the coefficients of p of x in the top row. So what's the coefficient of x squared? X squared's coefficient is 1, right? Coefficient of negative 3x is negative 3, and the coefficient of 2 is 2. All we want are the numbers in front of each term of the polynomial. Write the value of a, this thing up here, in this top left corner. So what you'll need to remember to do with this, we want the actual x value of the x-intercept. That's what we're kind of looking for. So this needs to be a positive one. You need to actually solve that thing. And then I have a little line drawn down here so I can find the answer after this. Then the first coefficient comes straight down, meaning that this is going to be 1. And then to work our way to the end, what we do is we multiply a, and remember a is up here, we multiply a by this number, and we write this below the negative 3. So what is 1 times 1? So we write 1. And then it says to add. Negative 3 plus 1 is negative 2. And repeat until you run out of space. Negative 2 times 1 is negative 2. What is 2 plus negative 2? 0. Believe it or not, we have just divided x squared minus 3x plus 2 by x minus 1, even though it doesn't look like it, right? Now, what happened is we took all the coefficients out of this. We need to put them back in. So the way that I like to draw this notation, I'm going to put a little box around this because this part right here is the remainder. Meaning that we got a remainder of 0, so we just found out x minus 1 is a factor of x squared minus 3x plus 2, which is probably something we kind of knew before we started because we know that x squared minus 3x plus 2 is factorable. Then when you go, you have to say, well, okay, well, what do I get when I divide these? First term gets an x to the 0. Next one gets an x squared. If I had more numbers, this pattern would continue. X squared, x to the third, x to the fourth, until you run out of numbers on the top. Meaning that when I did this division, x squared minus 3x plus 2 divided by x minus 1, you're going to get 1x minus 2 as the result. And we can do this longhand and see that. Let's see, we need x squared down here. So we know this needs to be an x. That's minus 1x. That turns into 0. Negative 3 plus 1, that's 2x plus 2. So that means this needs to be, I'm sorry, that's a negative. So that needs to be negative 2, which will give you negative 2x and a plus 2. And then when we subtract those, we get our remainder of 0, which is what we saw here. And our result was the x minus 2. It's the same thing. It's shorthand. Now, the reason this is going to be important for us is finding factors so we can find the x-intercepts of large polynomials so we can graph them is our goal. So we're going to use this method to test potential x values to see if they're x-intercepts so we can factor polynomials. But let's just try 2 of these together. So let's go through this setup. The big one is always p of x. This is always x minus a. So when we go to write this down, a goes in the top corner, coefficients on the top. So our coefficients are 1, 1, negative 9, and negative 9 from our p of x. What's our a value this time? Is it positive 1 or negative 1? Negative 1. Because you've got to just do this. Number that goes up top, you've got to take this, what you're dividing by, and solve it. So that means this one's going to be negative 1. Well, always pull the first term down. It doesn't change. And then we multiply. 1 times negative 1 is negative 1. 1 plus negative 1 is 0. And then we repeat. 0 times negative 1 is 0. Negative 9 plus 0 is negative 9. Negative 9 times negative 1 is positive 9. Negative 9 and positive 9 add together to 0. So is this a factor? Yes, because this number right here stands for the remainder. So that means I found a factor. And what's left over when I'm done with my division, I put these together. So that means if I did this division, I would get x squared plus 0x minus 9. And is it a factor? Yes. X plus 1 is a factor of that big p of x. And now you see why we label the bigger one p of x, because it takes a whole lot less time to write p of x in an answer statement than it does to write all of that out. Let's try the next one. Coefficients. 1, negative 2, negative 22, and 40, because this is our p of x this time. Let's figure out our number. We'll solve that. We get 4. Pull our first number down. So that one's 1. 1 times 4 is 4. Now you got to add those two things. Negative 2 plus 4 is positive 2. 2 times 4 is 8. Add negative 14. Negative 14 times 4. 56, and it's negative, right? And then when we add these, we get negative 16. And we run out of space, so we're done. So before we write down the answer, is x minus 4 a factor this time? No. Because we left with a remainder here. This is not a factor. And what we have as our answer, x to the 0, x to the first, x squared. So we get x squared plus 2x minus 14. And then we do have to remember, if we're actually doing division, how to deal with this remainder. You got a plus sign. This number goes on top of your fraction. What you divided by goes on the bottom, which was x minus 4. This follows the same rule that you would do. Let's say we did 3 divided by 10. Does that go in evenly? Is 3 a factor of 10? No, but you can put it in 3 times, right? And we're left with a remainder of 1. How do you write that answer, though? We write the 3 and 1/3, right? Because we have 1 of the 3 left over. The reason we write the plus here, we're actually saying the plus. We say the word and here. What is 2 and 3? 2 and 3 is 5. The word and actually means plus. There should have been a plus symbol in between that in your mixed numbers forever, but we never ever wrote them. Kind of weird, huh? But focus on the fraction stuff, okay?